Pavol. So thank you for being online. It's a great pleasure to have today Pavol Ševera, who's gonna tell us about Ricci flow in some unusual situations.
Yes, thanks a lot. I'll try to share the screen. Okay, probably it works, hopefully. Yeah, so this, to some extent, this is going to be some kind of pseudo-physics talk, so be gentle. Let me start with a two-part motivation.
Sorry, it's not a good time for a comment. I think since you said it will be a kind of semi-physics talk, you should be gentle, not us, right?
I'll be as gentle as it goes. Yeah, so let me start with some kind of two-part introduction. So the first thing is about just two-dimensional sigma models. So part one, two-dimensional sigma models. Just can you see well what I'm writing? And okay, things are going well. Okay, so what does one need for such a thing? So we need a manifold, which is in physics parlance called the target space, equipped, so it's M, equipped with a Riemannian metric G and with a two-form B. So this guy is a two-form. And we also need what is called a world sheet, so some two-dimensional thingy, a surface. Which is equipped with a Minkowski signature metric, or at least with a pseudo-conformal structure. So Minkowski. And then whenever we have a map going from sigma to M, so we have some F, then we can compute the what is the action functional of this F. So there's some action functional of this function F, which is whatever, it's integral over sigma of some expression. So there is like G plus B, and we're plugging in we decompose the differential of F in the light-like directions. So we put there like D plus F and D minus F, or we can split those two parts with G and B. So there will be part with G, D plus F, D minus F. And the B thing can be just written as integral of the pullback of this two form. Okay, that's all good. But now if people try to do it sort of on a quantum level or as a two-dimensional quantum field theory, so there is this, would be path integral. So we take EIS, integrate over F, integrate over all F's. And to kind of try to define this thing, one is to introduce some of the regularization or some of those stories. So there is some maybe scale entering into the game. And so okay, let me write regularization. And so what will happen in the end to make sense of this kind of expression of this would be path integral, one needs to have that G and B to be scale dependent. So it needs to depend on that cutoff that we introduced. And one gets this kind of what is called the renormalization group equation. So there is D over dt. T is the logarithm of the scale, whatever it means, of G plus B. But this thing is the Ricci tensor of the connection. It's a metric connection, so preserving G, but with torsion, which is given by TB. Okay, this is like a super beautiful equation. So it's some kind of slightly generalized Ricci flow in the sense that it contains also a two form, but otherwise it's just the one can say the usual Ricci flow. And since it's so beautiful, let me spoil it to some extent. So one can always add terms of the form. This is like what people call a dependence of the regularization scheme or something. So we can always just reparameterize the field, so to say, but introduce some infinitesimal diffeomorphism of M. So there would be a Lie derivative of, with respect to arbitrary vector field X, of G plus B. And one can also like spoil with another term, which simply comes from the fact that we're integrating B. So if you add to B something which is exact, it doesn't really matter. So you can also imagine there might be something like plus D of alpha, where alpha is this time a one form. Okay, so now we'll go to our Ricci flow. And maybe to add some little remark, as I said, that B is not really like fully needed. One can always add there something exact or something like that. It will not change really the action functional. So finally, what one can say that is really needed is that in place of B, usually people just use a closed tree form, so H, which is just locally equal to dB. So B exists now only locally. It's this H that exists globally. So that's a closed tree form. And then in place of writing this integral over sigma of f star B, you can imagine that now our sigma is the boundary of somebody. So sigma, you can imagine it's some kind of cylinder. And inside there is something that we might call Y. It's a three-dimensional manifold. So instead of that, we could write something like integral over Y of f star H. But then, like in true physics, what we really want, we don't want to have any Y filler thingy. So what one somehow really wants, we want to have a e power is well-defined, independent of any Y. And what one needs for that is really that in place of H, one needs to use what is called a differential character. So having a differential character is to some extent something like a little bit global in the manifold M. And so in this talk, I will simply be using always just simply those closed three form H. Okay, so this is the first part of this pseudo physics introduction. So far so good. Nobody complains, and there are still some people. Okay, so let me now pass to the second part of this pseudo physics introduction. Because the title is Generalized Ricci flow and Poisson-Lie T-duality. So what is this Poisson-Lie T-duality? So this is part 2. Poisson-Lie T-duality. Let me put it to parentheses. So first, what is ordinary T-duality? So that as those two-dimensional sigma models, usual or abelian T-duality is something which is famous and old and everything. So just T-duality. The idea is that one can have like, two different target spaces, so two different M's, which still give the same sigma model in some sense, or isomorphic or something like that. So let me start with the simplest example. So we would take our M to be a torus. So it is some vector space V modulo a lattice lambda. And G and B are constant. So G and B. So if you take the sum, one can view it just as an element of V star tensor B star constant. Okay, and we can now take the dual torus. So one can take the M star, which will be by definition V star modulo the dualities, lambda star. And now for what do we take for G and B on a M star? So for that, let's call it G star and B star. We simply take this G and G plus B, but we need to take the inverse so that it now sits in V tensor V. And the statement is that these two two-dimensional sigma models are isomorphic, give the same quantum field theory, two-dimensional quantum field theories, or two-dimensional conformal field theories in this case. So this give us isomorphic to the quantum field theories. Now, how does it go, or what enters into this game? This is slightly orthogonal to everything else I'm going to say in this talk, but still, let me tell you at least something. So, if you mention that this is our sigma, and we map it into whatever is M. Oh, it's a torus, so. That's our M. Then on sigma we can somehow cook up two closed one forms. One of them is closed one forms. One of them is simply df. So that's in omega 1 sigma with values in V, I guess, and the periods of f are in lambda. And there is another closed one form that one can cook up coming from the Netter theorem. So if f is a solution of equations of motion, then we would have something, let me call it whatever pi. This would be like momentum density. So this guy lives in omega 1 sigma V star. And classically, these periods are whatever, right? So the period when we integrate it along a circle on the cylinder that I drew here, that's going to be like total momentum. But quantum mechanically, there would be a quantization of those momenta because we have it comes from the action of the torus M. So that's like a compact group, and so we know what is one-dimensional representation, what they look like. So quantum mechanically, periods will be in lambda star. And so what does T-duality do? It simply switches these two things. Okay, so it's this kind of thing. The interesting stuff, perhaps here to say, is that it works perfectly on quantum level. This is a free field theory, so there is one can say everything about it. It's not difficult. Basically, if we describe it classically, then we know everything also on quantum level. But still, this T-duality is a true isomorphism only for quantum field theory. It is not true classically, because classically the periods of pi would not be just in lambda star, but would be anywhere. We wouldn't have quantization of momenta. So what we can say classically is that whatever, it's an isomorphism of not quite of Hamiltonian systems, but we need to reduce those Hamiltonian systems by the action of the torus, or that it's a Lagrangian relation between those two Hamiltonian systems. So it's not quite an isomorphism. One needs somehow quantization to get a true isomorphism. And maybe I should say also that in some sense, this isomorphism is non-perturbative. By non-perturbative, I mean in H bar. We cannot have H bar as a formal parameter, because with that, we wouldn't have this quantization of momentum. Okay. So I don't know. I'm just pretending that I know what I'm talking about, right? So everything's fine. Now, all of this, what I told you so far, is like a super famous stuff. Let me maybe add one little thing. So this T-duality was for the simplest case when the target space is torus. So more generally, people imagine having a torus bundle or principal torus bundle over some base, and there is some dual torus bundle over the same base. And then, okay, depending on whether that sigma model exists as a 2D quantum field theory, then people still say that we get two isomorphic quantum field theories. Okay, so now what is Poisson-Lie T-duality? This is still old, but slightly less famous, because this was my childhood project. So this is what we did with my advisor Ricci in the previous millennium, one of those previous millennia. And to really understand it well, one needs to know what is a Courant algebroid. Yeah, and this is now a tricky stuff. So I'm not sure, maybe shout at me if I should really explain what a Courant algebroid is. I will just say a couple of words, and if you're not satisfied, then somebody start shouting at me. So a Courant algebroid is, what is it? So one needs it's a vector bundle over some base and equipped with something. So there is a pairing on just on the fibers of E, and there is some kind of bracket on sections of E, and there is also a way how to go from sections of E to vector fields. So it's just a vector bundle map going from E to Tm, and I will just tell you what some two examples. So if M is a point, that means that our E is a quadratic Lie algebra. So it's a Lie algebra equipped with a invariant inner product. And there is another interesting case now when M is arbitrary. Sorry. So there are things which are called exact Courant algebroids. So how does it go? So if you have E, we have this map rho going to Tm. We can also take the transpose of rho, and using the pairing on E, we will have a map going from T star of M to E star, which is the same as E. And if that's an exact sequence, then this is what is called an exact Courant algebroid. So basically, an exact Courant algebroid is just Tm plus T star of M. And these things are classified by the third Drang cohomology, M. The bodies in R. Okay, so nobody's shouting at me, so it probably means that you sort of know or don't want to know about Courant algebroids. But we don't need to know much, just basically that they exist. Then there is one more little thingy, which is in a Courant algebroid, I should tell you what is a generalized metric. that's simply just a vector subbundle. It's simply V plus sitting in E, which doesn't satisfy kind of almost anything. The only thing that we need is that it should be positive definite. So when we take the pairing on E and restricted here, it should be positive definite. Positive definite pairing restricted on V plus. And when we take the orthogonal complement, I will denote it by V minus. So that's V plus orthogonal sitting in E. So this guy should be negative definite. Okay, very well. And so what is it, this kind of thing? Okay, if E is a Lie algebra, then it's just a vector subspace in a Lie algebra. But if E is, oh, let me write it this way. So if you have E, which is exact, and inside of that we have V plus. So such a pair is the same as a Riemannian metric and a closed tree form. On M. So yeah, basically what's happening that we can imagine that this E is T plus T star, and the V plus would be the graph of G seen as a map going from T to T star or something like that. Okay, so you see somehow the data which is needed for two-dimensional sigma model can be set, rephrased in this way that is the same as a generalized metric in an exact Courant algebroid. And the interesting thing is that, okay, so for that we then have two-dimensional sigma model. Okay. So what is happening now when we have V plus in E, which is now arbitrary? Well, it's no longer equivalent to any G and H, but still one can extract from this some sort of two-dimensional model. So two-dimensional, whatever, let's call it V plus sitting in E model. Let's put it in quotation marks. I will tell you a little bit later what that thing is. For the moment, just believe me that one can cook it up. It's for people who know those words, it's going to be some basically boundary field theory or boundary condition for the Courant sigma model. But what is interesting at this point is just the fact that we can generalize two-dimensional sigma models to this more general setup of arbitrary Courant algebroids. And so now we're going to Poisson-Lie T-duality. So what is it? With all this knowledge, it's going to be something slightly stupid. So Poisson-Lie T-duality. So the idea is that we start with a generalized metric in some non-exact Courant algebroid. So we would have something like E, who is over some base, and there is some V plus sitting inside. This is non-exact. It might be just a Lie algebra. That would be a perfect example when M is a point. And so imagine that this is some kind of ideal world. So this is not an exact Courant algebroid. So the model is not the ordinary two-dimensional sigma model, but we will now sort of cast a shadow from that and we'll get a true world. So how does it work? For that, we take another manifold, prime, with some projection. So this is probably like surjective submersion. And over M prime, we will take just the pullback of E. So let me call it E prime. which is over this. This guy is just P star of E. And the reason why I'm writing it as E prime and not as P star of E is that I want this E prime to be, again, a courant algebroid, and in a way which is compatible with the courant structure on E. So which means that if we pull back sections of E to sections of E star, then the courant bracket should be the same, and similar stuff. So now it turns out that, yeah, such a courant structure on E star might exist or might not exist, and it is not necessarily unique. So let's imagine that we pick one. So this is part of the data. So this is part of a choice that we equip E star with a courant structure. And then in E star we have naturally, sorry, in E prime we have naturally some of this V plus prime, who is just the pullback of. This is P star of V plus. Okay, and so what do we have upstairs? If E is exact, if, let's imagine that this E prime is exact. So upstairs we have just a metric and a closed free form on M prime, right? So it's a generalized metric in an exact courant algebroid. So we have a ordinary sigma model. Downstairs we have this strange sigma model, but the statement is that these two sigma models are equivalent. So these two 2D models are sort of isomorphic. So here we have isomorphic 2D models.
Pavol?
Yeah.
Can you spell out more precisely the conditions on these two courant algebroids?
Okay. Mm-hmm. So, yeah, let me try. So what we should for the bracket it's easy. So for the bracket we just if we take two sections, so we take P star of, I don't know, the U and P star of V, and compute the bracket in E star. So upstairs this should be the same as P star of the bracket. So this is E prime, and this is P star of U V, where the bracket is computed in E. So this is one condition, and okay, then one can say the same condition on the pairing, but the pairing, one can say, is simply pulled back to E prime. What is slightly less obvious is how it works with the anchor map with rho. So it's something like that if you take P star of some section of E and then compute the anchor in E star. So now we have a vector field which is on M prime. So I can say directly that it's equal to rho E of U, but the condition is that if you now project it, E star of this guy should be equal to that thing. So those are the conditions. Is it okay?
Yeah, thanks.
Okay. So okay, so now as I said, the story is that we're getting somehow two isomorphic two-dimensional models. I should say this isomorphic is in a little bit in quotation marks, because this is, let's say, this is a classical story. So it would be more like some reduction of one of them, of this thing which is upstairs, is isomorphic to the one who is downstairs. So there is a hope that if things are chosen in the right way, and if like we do it non-perturbatively, then it will give a true isomorphism. But here we just cannot claim it. Okay, and but who cares about those generalized two-dimensional models? So the true thing is now that if you have another target space, double prime, and there is some, maybe this is P prime, this would be P double prime, and here we take E double prime, and inside V plus double prime, sitting like that. Then, okay, we have now two true 2D sigma models. Both of them are isomorphic to some kind of strange two-dimensional model. Therefore, they are isomorphic. So these are isomorphic to the sigma models. And that's Poisson-Lie T-duality. So let me get to some examples. Oops. So I'll start with the case when M is a point. And so our E is just a quadratic Lie algebra. So how does one get those pullbacks in a way that, that they are now exact Courant algebroids? So the way to go is that we take a Lagrangian Lie subalgebra. And then for this M prime, where was it? This thingy. We simply take, okay, we need to choose those groups, but we take like G modulo H. So E prime is simply, what is it? It's just G times G over H. Or what is as a Courant algebroid? Well, the bracket of two constant sections is just the bracket in Lie algebra. And the anchor map is the action of G on G mod H. So that's it. That's a nice Courant algebra, which is exact in this case. And now if you choose two different H's, sorry, I know that H was a closed tree for now it's a group, but it happens. So if you take two different H's, we get that duality. So this is somehow the case with no spectators. Meaning that M was just a point. And the second example, which sort of is the most general example, is not true, but morally it's true. So let me just say something. So this was one example. The second example is that we start with a principal G bundle. We still have the G, which was there before, a quadratically algebra G and some group. So let's say principal bundle. And we need a, this would be first Pontryagin class corresponding to the inner product, to the pairing on G to be trivial. So we need that if we take the curvature of some connection, so that this form should be D of somebody. And if you have such a story, then again, this M prime would be simply P modulo H, and different choices of H's will give us then like M prime or M double prime, and these are then well, somehow in Poisson-Lie T-duality. Okay.
Pavol?
Yeah.
Sorry, just to make sure, the Courant algebroid is the trivial Courant algebroid of M prime, or what is you say this would be an instance of?
This is okay. Let me say something. This is an interesting story. Yeah, who cares about the Ricci flow? So let me tell you something about this. So the story is that having this setup that I wrote here, from that one can cook up a exact Courant algebroid over P. So this is over P now, but which comes also with a somehow embedding of, or there is a map from, okay. G is represented by sections of this EP. And whatever the pairing on G is the same as the pairing is the one which is in EP, and it's like a lift of the action of G on P to some kind of Courant representation, something like that. So this kind of setup is equivalent to that setup where we have like we have this vanishing first point eigenclass together with a choice of a primitive, and so that's like a little exercise to do it. It's not difficult. So this guy, you simply write that it's like T P plus T star of P, and then do your business. So, and then this E who is over M, that's the reduction of EP by this action, by G. And also that E prime, which is over M prime, is the reduction of EP by H, but it's only for people who know what Courant algebroid reduction is, which I will not tell you. Is it okay? No, Anton
Yep.
doesn't respond.
Yeah, yeah. It's okay.
It's okay. Okay. So this was a super long introduction about Poisson-Lie T-duality. But what this talk is about is this generalized Ricci flow. So now the introduction is sort of over. So this part 3. Generalized Ricci flow. And say the motivation or the question one asked is that is this Poisson-Lie T-duality compatible with the renormalization group flow, with the Ricci flow? So is PLTD compatible with the Ricci flow? Right, so we have we have two target spaces, M prime and M double prime, equipped with some G and B, and some of the other one is equipped with some G and B. So we let them now flow with that Ricci flow, and if there is any justice, then they should stay in, like they should still keep it being Poisson-Lie T-dual during that flow. But how can one show it? So it's like a super simple thingy. So the idea is simply to find this generalized Ricci flow, a flow for now arbitrary generalized metric. So where this is no longer exact. Not necessarily exact. So just try to extend the Ricci flow, which is given just for V plus who sits in an exact Courant algebroid, when this is equivalent at least locally to G and B, to this kind of situation. And let's say, and make sure that it's compatible with pullbacks. So compatible with pullbacks. So if it's like that, then now kind of by definition of that Poisson-Lie T-duality, it's going to be compatible with the Ricci flow. So this would imply the answer is yes. So now the question is how to find a suitable flow for V plus sitting in a Courant algebroid. So what should it look like? So now this V plus should move. So there would be like equation. I write it slightly schematically. So how does V plus move inside of E? So there should be some like generalized Ricci, the V plus. And that should be a map going from V plus to V minus. So it should somehow show us how the V plus that sits inside of E, how it moves, and an infinitesimal deformation can be seen as a map going from V plus to the orthogonal complement, right? So we just modified it slightly. So it's like super easy idea. Everything should work. The only problem that it doesn't exist. So there is like this minor trouble that no such thing exists. So but it's not a big deal. So what one needs to do is that we need to choose something. We need to impose some choices. What we did with Friedrich that we originally is that we chose a connection. So plus a choice. But then Mario Garcia Fernandez found out that it's way better to choose something which is called a divergence. So, okay. Divergence, which is let me write it what it is. It's a map, linear map going from I mean just our linear map going from sections of E to functions, and which satisfies that divergence of a function times a section is the same as f times divergence of U plus a row of U acting on F. But if it sounds like too abstract, we can simply choose a connection. That's perfectly good. And the nice thing now is that, yeah, unfortunately we need to pick a choice, but fortunately the corresponding flow is depends on the choice only through automorphisms of E. So there is like thing that different choices differ by infinitesimal automorphisms of E, actually inner. So things that look like that we're just acting with somebody. Okay, so that's why it's somehow nice that, okay, let me go back, sorry. I will go back very far, very, very, very far. Ah, here it is. You see, here was this Ricci flow. Oh, let me maybe. And I added there those two totally useless terms, like this Lie derivative and plus that d alpha. But what it corresponds to is exactly that we modify this nice Ricci flow, which is given only by the Ricci tensor, by an inner automorphism of our exact Courant algebroid, which is a pair, a vector field, and a one form. Okay, so this all sounds like a fairy tale. I should maybe put up. So I should tell you what this generalized Ricci thingy looks like. Yeah, maybe before going there, I should probably tell you that, of course, with Friedrich, we thought that we were doing something like totally new that nobody was ever interested in and nobody would be interested in. But when we finally got there, it turned out that there were like not quite hundreds, but maybe tens of people who already defined their generalized Ricci thingy. So the names are Coimbra, Strickland, Constable, Waldron, and Yurcho and Visoki and Garcia Fernandez. The last two names were just a single person, so it's not so bad. So our work in the end was just this, maybe like to do it for arbitrary coherent algebroids. I'm not sure whether it was done before, but also to come up with this idea that, yeah, those choices make things kind of difficult, unnatural, but actually the thing depends on the choices only via those inner automorphisms. So that's why those choices are totally immaterial. Okay, so before the break, let me tell you what is this generalized Ricci thingy for in the case when M is a point, and so E is a Lie algebra, and in that case, like this, for divergence, I would just take 0. It's perfectly good choice. So to say, no choice is needed in the case of M being a point. It's only when M is non-trivial when I need some choices. And this Ricci thingy. So what is it? We should take somebody like U plus who is in V plus, and it should map it to somewhere something which is in V minus. So let us pair it with such a thing. So I'll take V minus in V minus, and the thing is like this. So we take V plus. Now this vertex is the structure constants of G. Here we put the orthogonal projection to V plus. Here we take orthogonal projection to V minus. Again, structure constants, and there is V minus. Maybe there is some sign, but doesn't really matter. It's a nice expression. Now for general E over general M, the thing differs simply by adding some divergences. I will not tell you what those terms are, because after the break, I'll tell you something better. So I don't know, it's probably like the time to do break anyway.
Yeah, sounds good. Thanks a lot. Any questions before the break?
Pavol,
yeah.
Does this different choice is differ by infinitesimal automorphisms of E, which is nothing but the Lie algebroid, ATIA Lie algebroid? Does it mean something?
Yeah, just probably what you said. Or you see, what's really happening? So with those, if for those choices, we take those divergences. It's in many ways it's a nice way to how to put it. So if we take it like that, so if one thinks about what is the difference of two divergences, so then this like a term that differentiates something will disappear. So two divergences really differ by two sections of E star, or one can say by two sections of E, because there is a pairing on E, and that. So if you take those two choices, then those two those two flows will differ by an inner orthomorphism, which is given by a section of E, right? And that section of E is, well, it's the difference of those two divergences, but okay, not quite. One is to project that then to V plus. So something like that. There is some, the formulas become really nice when one uses divergences for those choices and not a connection. But that's a slight technical point. So I don't have like a really nice answer to your question.
Well, need to think. Thank you.
Any more questions? Well, if not, thanks again, and we make a 15-minute break. So we resume at 4:05. So see you soon.
Okay. In the talk, so he's called actually Valach. That's okay. And now, so far I told you there is some kind of generalized Ricci flow for generalized metric in arbitrary Courant algebroid. And the next part is about, okay, it's called dilaton, or is it a gradient flow? So it is like kind of maybe for understanding better that flow, it's a reasonable question always to ask whether for a suitable choice of a metric, whether it's a gradient flow that would say something about the flow. But also for more stringy applications, people are not really only interested in like Ricci flow, they want to have fixed points of Ricci flow, but not just that, they like want to have something which is called a dilaton and things like that. So let me get to it. The first question one can ask, so this generalized Ricci thingy depended on some unnatural choices, as I told you. Finally, the dependence was immaterial, but it did involve unnatural choices. So it's a natural question to ask, so is there something really natural given by just generalized metric? So sorry, let me change the color. A natural.
May I ask a kind of naive question? Mm-hmm. So you said that so the equation without the choice of the divergence does not exist, right? There is no natural equation. Mm-hmm. What does it mean precisely, right? When you say it does not exist, then like it's some statement about tensor calculus, right? That you're making, or what?
Like, so you're basically asking whether it's a theorem.
Or I mean, like maybe if I wanted to make it a theorem, however weird, how would I do it? Yeah, is it some kind of theorem?
It's just me saying some random stuff, I would say. No, I think like it is a theorem, but we probably never formulated it, and even less we proved it. It just basically, whatever, looking through the stuff, it just showed up that there is no natural definition. So just I was trying to fake it and trying to tell you something as just truth, but maybe somebody should write it down more precisely.
Okay.
So yeah, you got me. Anyway, so back to this business. So we're looking for something natural given by V plus inside of E. So a natural object given by a generalized metric in an arbitrary Courant algebroid. And that would be somehow, that would contain inside in some way this generalized Ricci thingy, which does involve some choices. So how to do it? So the thing which is natural is some kind of Laplacian. So it's a formally self-adjoint, self-adjoint second order differential operator, formally self-adjoint on an arbitrary manifold that should act on half densities. So on half densities. Okay. So it exists. There is one can write down a nice differential operator. This time I will write you a formula. I'm not sure how much happy you're going to be about the formula. But just to show you that we have also some formulas. So the thing is, first of all, so what is the symbol of the second order differential operator? So the only natural thing is basically you would take the pairing which is on V plus and push it down to Tm. And so a differential operator having this kind of symbol is, okay, there is coefficient 4, which is for whatever reasons, doesn't really matter, and times the Lie derivative with respect to okay, we need to choose a, say, orthogonal frame of for V plus. Sorry. So there's some kind of basis of V plus. There is the pluses correspond to that thing, and we take it twice. E plus A. Okay, this is definitely a self-adjoint, formally self-adjoint operator, but it will depend very much on the choice of that frame. So it's not like naturally defined. But anyway, whatever should now follow should be just a function to keep it formally self-adjoint. And that function is, I'll write it down schematically because that way it's nicer. There is 1/2 plus minus plus and this thing. So what does it mean? Here we have somehow structure, not really functions, but sorry, not really constants, but functions of our Courant algebroids, things that are like whatever U, V, W, these kind of things. But where for U, V, and W you pick things which are in our frame, and plus and minus are again like projections to either V plus or V minus. And then there is 1/6 and times just pluses. Now, yeah, this is not a very nice definition because I'm saying that as it's written, it depends horribly on the choice of the frame. But then one can, with a simple calculation, one can show that actually it's independent of the frame. Now, here I don't have a good theorem saying that this is the only thing that one can write down. But in some sense, yeah, it's difficult to write down a universal expression that would in the end be independent of the choice of the frame, and this one works. There is a natural question like what it is actually. So where does it come from? How to write it down naturally? And strangely, we just don't know. What we do know is that when V plus is entire E, okay, then it's not really positive definite, but it doesn't really matter. So that's fine. So if for V plus we take the entire E, then this second order differential operator is actually a function. So those derivatives, they pretend to be, but in reality they are. Well, they act simply as multiplication by a function. And that function is the square of the generated Dirac operator. For people who know what it is, what the thing is, and some of them do, I know. But for a non-trivial V plus, so when V plus is a true subbundle, not either 0 nor entire E, then I don't know a good, better definition of this thing. Just believe me that this one is invariant, so it doesn't depend on the choices, on the choice of the frame. Now, what happens, say, if E is exact, and therefore V plus is the same as a pair G and H? So in that case, this delta V plus is going to be just, okay, there is factor of 2 times the ordinary Laplacian given by our metric, well, acting on half densities, and plus some function. So that function is minus 1/2 times the scalar curvature of our metric, and plus 1/4 and times, well, when you take square of H, which I mean that you somehow contract 2H is using the metric. Okay, so that's it. At least for suitable values of 2 minus 1/2 and 1/4, this should be true. And this is a rather famous expression. So let's call this one. Okay, let me just call it S, which depends on V plus and on a half density. So this is a half density. So we write something like -1/2 and half density sigma times another half density, which is just this Laplacian applied to sigma. So this guy is the what is called the string effective action, or low energy string effective action, or a supergravity action, or something. So more precisely, what one needs to so if you know if you heard about those things, so what one needs to plug in is that sigma is exponential minus phi, where this guy is the dilaton, and times the metric half density. Right, so phi is the dilaton. Okay, very nice. So in the case of exact round algebra, this is something which is like very useful or central in string theory. Which I don't know anything about string theory, but still, I can still use those words, or one can say it's a supergravity action, where the things that enter into reduction are the metric, the closed tree form, and the dilaton. So those are the fields that enter there. But now we have it for arbitrary Courant algebras. Meaning we have it for arbitrary generalized metric in an arbitrary Courant algebra. Okay. Now I can with this now I can say that first of all that this generalized Ricci flow is a gradient flow. So how does it work? We need to choose a everywhere non-zero half density. Which, by the way, then given a half density, then we have also divergence, right? So this divergence of any section will be defined, or with respect to sigma, would be something like that we take the Lie derivative of sigma with respect to the vector field which is associated to u, and then we need to take like sigma inverse, and maybe because sigma is a half density, we should multiply it by 2. But anyway. So we choose such a thing, and now on the space of all generalized metrics, so on the space whatever M of generalized metrics in arbitrary fixed Courant algebra, what we have. So we have a function which is just this action functional. So sigma now is fixed, right? So we pick that one, so now it depends on V plus. And we also have a Riemann metric, which is, so I should tell you, if you take two infinitesimal deformation of V plus, so what is it? Well, if you just pair two deformations of V plus, we get a function on M, so then we need to multiply with the density, which is sigma squared, and integrate it over M. Okay, so that's it. Probably there is a sign minus to make it positive definite. And it turns out now that this Ricci flow for the divergence which is given by the by sigma is the same as the gradient flow of our function as v plus sigma. So this is one thing, and a closely related thingy is that what are the Euler-Lagrange equations or equations of motions? Euler-Lagrange equations of S v plus sigma. So this is an action functional now with two fields, one can say. So there is v plus entering and sigma entering. So one of them is that that's when we take the variation with respect to v plus. So from that we obtain that the generalized Ricci thingy for the divergence which is given by sigma. So let me like write it here with sigma. This is equal to 0. And the second equation, which is like easier when we take the variation with respect to sigma, is that the Laplacian of sigma is equal to 0. And yeah, so in case when P is exact, then these are the supergravity or string background equations. Okay. So now a natural thing to ask basically is whether Poisson-Lie T-duality is compatible with the supergravity equation. Yes.
Paul, just a question that some participants were telegraph typing to me. So how is it if you're using that word sugra? Yep. Shouldn't it also have some fermions, or what's the meaning?
Oh, definitely. Yeah. So I shouldn't be using that word probably. It's like this is only the bosonic part, and only for whatever this may be like. And also I might be missing some depending now on which type of sugra one takes. So I would be also missing probably some.
But there one can put all those fermions equals 0, and then you get what you.
Yeah.
So in particular, solutions that you would be finding with the equations that you're writing, they will be sugra solutions, or not?
Yes. Yes. Oh, yeah. With 0 fermions.
Yeah. Okay. Thank you.
But maybe like those whatever string background equations, it might be less controversial. I don't know, or more. Not sure. Okay, so now the natural question is: so is this Poisson-Lie T-duality, or which is simply all this story about pullbacks of Courant algebras? There is nothing more to it. The definition, that's the definition of Poisson-Lie T-duality. So is it compatible with supergravity or string background equations? And the answer is okay. So let me write it. So is PLTD compatible with this sugra thingy, supergravity equations? So yeah, these are the equations basically. The only problem now is that what was the setup for Poisson-Lie T-duality? So the idea was that we had one non-exact Courant algebraic sitting over some M and V plus inside, and then we had a pullback. So this was, there was some submersion P prime going from M prime to M. And if you imagine that here we also take now sigma. So we have two fields, V plus and sigma. And if these two fields satisfy our equation, so if sigma v plus would be this generalized Sugra solution. By generalized, I mean like these are equations for a general Courant algebroid. One should call them probably generalized supergravity equations. So it's only when E is exact when those are like ordinary supergravity equations. So now the problem is with the dilaton, right? Because here we have this sigma, and we cannot. Sorry, this was the prime. We cannot just so easily pull it back upstairs. But if you do it like in the simplest way, so if one imagines that they do have some tau that would be fiber-wise half density on the fibers of p prime. Then we could pull it back simply by, like, we pull back sigma and then multiply it with tau, right? So we can then take p prime star of sigma and times tau. That's a half density. But now the problem is whether this operation is compatible with the action of the Laplacian. So whether it is true that if you first act with the Laplacian and then pull it back, whether it's the same as if you first pull it back and then act with the Laplacian, and that would be okay if tau is invariant, which means that what does it mean? Probably something like that. If you take any section of E, now pull it back, E prime star of that thing, now, and compute the Lie derivative of tau with respect to that this should be 0. Then the pullback of sigma and v plus to some sigma prime and v plus prime. So this is our sigma prime. So this will be now automatically a solution of supergravity equation. So to finish off this story, sorry if it's a little bit confused. So when does tau exist? Say in the case when M is a point and M prime is G mod H. Now you see tau is simply going to be a half density on M prime. It's a fiber-wise half density, but here it's just simply half density. And invariant means that it's G invariant. Yeah, it's invariant with respect to constant sections of our Courant algebroid. So in this case, we need like G invariant tau, and such a thing exists if and only if H is unimodular. H is unimodular. And for more general M, there is a similar story saying that if you interpret this pullback in terms of some say some Dirac structure, for people who know about what those things are, then the statement would be that tau exists if and only if that Dirac structure is unimodular. So there is a little bit of trouble with trouble here. So it's not true that Poisson T-duality is always compatible. So there is some trouble with the dilaton. And in general, there is some, I can just say it in some words. So in general, if one, instead of half densities, simply uses general divergences, those strange things, then it also exists in the physics literature. That it's called modified supergravity. Okay, so which means that Poisson T-duality is always compatible with modified supergravity, but for true supergravity, for having a dilaton, one needs to have an invariant half density. I should also say that basically is for a similar result or one kind of equivalent was obtained by also by Ricci and Bisoki. Okay, so this was some small excursion into something, again, something that I don't understand, into whatever string theory. And now, okay, I still have some time. So let me now tell you a little bit about that strange two-dimensional model, which is given by a generalized metric. So when it's not in a exact Courant algebroid, but in an arbitrary Courant algebroid. So it's now section 5, Poisson-Lie, T-duality, and its higher analogs. Via boundary field theories. So I will now tell you something like super general. So for Poisson-Lie T-duality, we have n equal to 2, but I will tell you something that works for arbitrary n. So it might be, we'll be talking about n-dimensional field theories. So we need a topological field theory. So alpha is a n+1 dimensional topological field theory. Typically, say for n equal to 2, one would take, for example, Chern-Simons, or this slightly less famous and whatever less existing thing called Courant sigma model. Okay, then we take an n-dimensional sigma, typical with a metric, whatever Minkowski or Riemannian, whichever happens. And now we consider alpha on sigma times an interval, so alpha on sigma times I, which is like the unit interval, 0, 1. So it's something like this. Let's say that this direction is sigma, that direction is I. And so now we're putting this topological field theory on a manifold with a boundary. Say, imagine we're taking Chern-Simons, but on something three-dimensional with a boundary. So we need to specify some boundary conditions or something of that sort. So on one side, say on this side, let's pick up some topological boundary condition. Topological boundary condition that I will call L. And on the bottom, now that's the interesting thing. Then here we take a non-topological boundary condition, non-topological, physical, if you want, boundary condition or boundary field theory, the same thing, that I will call F. Okay, so there is like alpha, the Chern-Simons is inside, and with some thing is happening on the boundary. On one side, the thing is topological, so it's all nice. On the other side, it's very unnice. It's non-topological. This thing can be understood. It can be seen as a. So this is a just n-dimensional field theory. Non-topological because part of the boundary condition is non-topological. Now, this idea of the general duality, so to say, is to keep alpha and F, this non-topological thing, fixed, and change or choose different, use different choices, change L. So if we do it, we in principle are getting a different field theory, but okay, this is now some hand waving that they differ only through some topological nonsense. But what's happening in ordinary T-duality? So there is something. Let me cite some authorities. Kapustin and Saulina. So for abelian Chern-Simons. So if you take Chern-Simons with an abelian group, so with the torus. So what's happening that classically there are many topological boundary conditions. Just basically any Lagrangian subtorus in our torus would work as a classical boundary condition. And it does also on the quantum level. Yeah, those things just are perfect. But when we quantize it, then those classically different boundary conditions become the same quantum conditions. So actually for the torus that we are actually using here, it would be that all classical topological boundary conditions coincide on the quantum level. So now this is one explanation of T-duality. Now that we would be using this kind of stuff with abelian Chern-Simons and with arbitrary topological boundary condition and fixed non-topological boundary condition. So classically, we're getting somehow different looking classical models, classical field theories, but on the quantum level, they are just the same. Let me put there somehow, okay, maybe I made it somewhat too mysterious. So let me explain what's happening in Poisson-Lie T-duality. So therefore, alpha, let's say with no spectators, no spectators. For alpha, we will take Chern-Simons with this quadratic Lie algebra that was appearing all the time. And for who is now F? F is that non-topological boundary condition. So that's given by our generalized metric. And the condition is that A sits in omega 1, 0 sigma with values in V plus omega 0, 1 sigma with values in V minus. And if you're doing it like in the Button and Vilkovisky setup, which is the right way how to put it, so there would be also omega 2 sigma with values in G. So that's how we restrict. So this is now this form with values in G when seen on the boundary is not an arbitrary form, but it needs to satisfy these kind of conditions. And this L thingy would be simply that we pick H in G Lagrangian Lie subalgebra, and we would now have that A is in omega sigma with values in H. Okay, what is maybe kind of surprising, not so clear, that if we do this, so if we impose these two boundary conditions, so what's happening here? We have our, it's just Chern-Simons. On one side, we impose this boundary condition with a generalized metric. On the other side, we impose the boundary condition given by a Lagrangian Lie subalgebra. The thing is actually equivalent to a two-dimensional sigma model. This model is the same thing as two-dimensional sigma model with target which is equal to G mod H. So this is equivalent to a two-dimensional sigma model with target G mod H. And if we pick a different H, then we're getting a different sigma model. And we're sort of hoping that on the quantum level, hopefully those two topological boundary conditions will coincide if they are chosen in the right way. So then we will have a true equivalence of two-dimensional quantum field theories. Okay, so I probably don't have too much time. So what I wanted to say, but let me now just say it in a couple of words, that is that this general setup where n is arbitrary, not necessarily equal to 2, contains in an easy way, say, electric magnetic duality in 4 dimensions and similar things, and some like really strange looking duality. So these are now dualities of gauge theory. So if you go to higher n, we'll automatically be getting through the BV formalism some gauge theories, or maybe even higher gauge theories. They maybe don't contain all the dualities that we would like to see, but okay, that's life. So let us stay just simply with this Chern-Simons picture. And the very last thing that I wanted to tell you is so how it fits together. What I mean by that. So, this previous, just this section 5 of my talk with this topological field theory and I don't know what, it looked like totally orthogonal to everything that happened before. Right? Before we were talking about some Ricci flow and I don't know what. This is a thing which is not done yet, but let me still tell you something. Also, naturally I forgot to say that this thing was joint work with still with Friedrich. And also Jan. So this thing that I was telling you about, this general picture of how to get dualities. The part 6 is probably joint work with once it starts existing, that it will probably joint work with several people, but at the moment it's not real work. So so the thing, if we what I wanted to tell you, so let us consider this Chern-Simons theory with G, and with the boundary condition, with this non-topological boundary condition with BC, which is given by that A is in omega 1, 0, sigma values in V plus omega 0, 1, sigma with values in V minus, and plus just omega 2 sigma values in G. So we have no idea about how to make that Laplacian appear, but at least how about this generalized Ricci thingy? So the idea is that it should simply be the renormalization group flow for Chern-Simons theory with this boundary condition. So RG flow, it should be that expression that I gave you before. It should be given by this kind of thing where now this sits in V plus and this sits in V minus. So the thing that is flowing, that should be flowing, it should be V plus moving inside of G. So it should be like the subspace, and it should depend on the scale. It might sound a little bit strange that Chern-Simons, which is like a beautiful topological field theory with all the Feynman integrals simply convergent, would produce any randomization group flow, but the boundary condition is non-topological, so then maybe it's not so surprising. And so what is the wishful thinking? So we need to pick a, say to write down some kind of perturbative quantization, we need a propagator. So what is normally a propagator would be some, okay, let's call it P. It's a two-form. Let's say Y is our three-dimensional manifold in Y times Y with a singularity on the diagonal with values in G tensor G, and such that dP is the delta of the diagonal, like this drum current, and times T, and by that thing I mean just the element in G tensor G which corresponds to inner product. And for the usual Chern-Simons, say in R3, one can now just pick a very nice propagator and then everything simply converges. But here we need to observe these boundary conditions. So we need to stay like that. So here our propagator, it actually will be of the form so it will come in with two parts. So there will be like omega plus tensor T plus and plus omega minus tensor T minus. You see why I'm writing in this way. So this guy is the inner product on V plus inverse, and this guy is the part which is in V minus. And now this V plus and V minus, they must satisfy reasonable boundary conditions. So they might show that in the end we have these kind of fields. So that we have our boundary condition that we imposed. So this one. Okay. And so if we do it, if that propagator is now split into two parts, so these are just differential forms, omega plus and omega minus, and T plus and T minus are the parts that live in the Lie algebra. So now when we start drawing Feynman diagrams, so there will be some trivalent graphs, something, whatever, something. So then basically we now need to put on every edge, we need to write plus or minus, and then take the sum over all signs. Minus, 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 let's say something like that. Right, so this is what it would look like. So for each such a diagram, we put there omega plus on each edge with plus, or omega minus on each edge with minus. Compute the integral, and then we will also compute the corresponding expression in the Lie algebra. So we would be putting T plus on each plus edge and T minus on each minus edge. And structure constants on in the vertices. Okay, so this is what would happen. And now it looks like trying to write down those expressions for omega plus and omega minus. It looks like the only divergent one loop diagram that it's okay. That is this one. like that. And there is plus and minus here. So if one takes two pluses or two minuses, then, and we take the wedge product of those two forms, then things will converge. And here we also need to take plus and minus like that, which is, if one compares it with what was here, it looks exactly how that generalized Ricci flow. So this is like the first hope about how to make things fit together. It should still be done, at least on some physics level of precision. And it should be then extended to arbitrary Courant algebra, so not just for Courant algebra is over a point. There it also looks reasonably likely that we'll be getting exactly those divergences that we need. And then one should also try to understand what's happening with this Laplacian. And there I have just no idea. Okay, so this was like a very confusing end of this talk.
All right, so thanks a lot. Any questions or comments?
I have a question.
Yes.
So for general grand algebra, the thing that you did for the Lie algebra, where you just computed evaluated the Feynman diagram with the structure constants would turn to what?
Okay, so then the thing is what is called the Courant sigma model. And
Okay.
now now there are yeah, it's an AKZ model, and there are right. So the thing that we have there now is there are like those structural functions. So C, I know A, B, C, and times something theta A, theta B, theta C. But plus there is another term which is just, this depends on axis. And there is another term which depends again on, I'm calling it A. So this would correspond to the anchor. And there will be like something like theta and psi. So so now there are fields that correspond to thetas. There are also fields that correspond to those xi's, and there is a vertex for going between theta and xi. So the diagrammatics is slightly more involved, but there is only this one type of vertex of this form. So yeah, no, there will be basically only one additional diagram. Now I don't remember what it looks like. It was something like this, and then this thing. Now there is this A thingy, and it becomes now that like this psi thing. It just reconnects like that.
Okay. More questions or comments? I got a somewhat naive question about those diagrammatic calculations. So how is it so this stuff so they would be in some way attached to the boundary, right? Or those diagrams. So how does it work? Right, it's a boundary effect, as you said, because in the bulk it is topological. So how is it taken into account in your diagrams?
So in these diagrams, it was right. So it depends now what we're computing, whether we're computing just the partition function or whether we want to have also some correlators.
Mm-hmm.
So
I thought you were computing this running of V plus, right?
Right, but for that I simply was basically yeah, maybe I don't understand the thing well enough. That's first thing. Yeah, so in principle, if I draw a diagram like that, then there is somebody sitting here and somebody sitting there, and so those would be some kind of things close to the boundary. But in this setup, it's not really that we have like boundary fields. some special boundary fields. Everything is, the only field that is there is that A, which is happening in the bulk. Just on the boundary, it has a boundary condition. It needs to satisfy boundary condition. Otherwise, these diagrams, yeah, they're really happening entirely in the bulk. The only thing somehow that enters it is that those integrals start being divergent when you try to integrate it also close to the boundary. And it is like that. So those that omega plus and omega minus that I still don't understand properly, but at least we know to some extent what it looks like. So they produce integrals that do have ultraviolet divergences close to the boundary. Probably doesn't answer your question, but it's the best I can say.
I mean, yeah, sounds good. Any more questions or comments? Well, if not, say thanks a lot. Yeah, right. So thank you very much, and so see you at the next seminar. So you saw in the announcement there are 2 more interesting seminars this week. Among them, this Global Poisson, taking place for the first time on Thursday, and I'll send the announcement for next week's seminars soon. So
thank you.
Thank you.
Bye-bye.
Bye.